A mining truck can be taller than a house and carry more weight than hundreds of cars. But why build something so enormous when a fleet of smaller trucks seems cheaper and more flexible? Most people assume bigger simply means stronger. The real answer is hidden in wasted rock, loading cycles, traffic, fuel, and a surprisingly fragile limit beneath the machine itself. Subscribe for more hidden engineering stories, because these trucks are not gigantic just to carry more, and the reason they grew this large changes how you see the entire mine. Most of the payload is worthless. When you see a mining truck carrying hundreds of tons, it is easy to imagine that every load is packed with valuable copper, iron, or gold-bearing rock. But often, the exact opposite is true. Much of what these machines move is waste rock, the enormous layer of material sitting between the surface and the ore body below. Mining companies measure this problem using something called the stripping ratio. A ratio of 1:1 means 1 ton of waste must be removed for every ton of ore recovered. In some mines, that ratio can climb much higher, potentially approaching 10:1. So before a mine can process one valuable load, it may have to haul away several loads that produce no direct revenue at all. That changes the economics completely. The challenge is no longer simply extracting valuable minerals. It is moving an entire mountain as cheaply and quickly as possible. This is why using ordinary dump trucks would be disastrous. Each small truck would carry less waste, make more trips, require more drivers, and spend more time loading, turning, climbing, and unloading. The mine would burn money moving material it cannot sell. So the giant truck exists because the cargo is often nearly worthless. The larger the load, the fewer expensive trips the mine must make before it finally reaches the rock that matters. The shovel chooses the truck. A mining truck may look like the star of the operation, but its size is often decided by another machine entirely: the shovel. Modern electric rope shovels and hydraulic excavators can lift extraordinary amounts of material in a single pass. The truck waiting below must be large enough to receive those loads efficiently. If it is too small, the shovel may fill it in only 1 or 2 scoops. That sounds fast, but it creates a new problem. Trucks must constantly pull in, load, pull away, and make room for the next vehicle. Every exchange costs time. And when the shovel is one of the most productive and expensive machines in the mine, even short delays matter. Mining companies therefore try to match the capacity of the shovel with the payload of the truck. A common target is to fill a truck in roughly 3 to 6 passes. The Komatsu 4800X PC rope shovel, for example, can be configured to load an ultra-class truck carrying about 363 metric tons in only 3 passes. That relationship explains why mining trucks became so enormous. Excavators kept growing because mines needed to move more material. Once each bucket became large enough to overwhelm a smaller vehicle, the trucks had to grow with them. The truck is not simply built as large as possible. It is built around the rhythm of the shovel. And that rhythm controls the entire mine. The mine buys tons, not trucks. A giant mining truck can burn an astonishing amount of diesel. It requires specialized mechanics, enormous tires, reinforced roads, and equipment that may cost millions of dollars. Judged like a normal vehicle, it seems wildly inefficient. But mines do not measure efficiency the way a car owner does. They do not ask how much fuel one truck burns. They ask how much it costs to move 1 ton of material. That is the trick. Imagine replacing one ultra-class truck with several smaller vehicles. Each smaller truck may consume less fuel by itself. But the mine now needs more drivers, more maintenance crews, more engines, more tires, and more loading cycles. More vehicles also mean more time spent waiting at shovels, fuel stations, workshops, and dumping areas. Loading and hauling can account for a major share of the cost of open-pit mining. In some industry examples, these activities dominate the primary mining stage. That makes cost per ton one of the most important numbers in the entire operation. A Caterpillar 797F can carry a nominal payload of 400 U.S. short tons, or about 363 metric tons, in one trip. Its fuel bill is enormous, but that number means little without the payload beside it. A machine can consume more fuel per hour while still using less fuel per ton moved. So the mine is not really buying a truck. It is buying fewer trips, fewer delays, and a lower cost for every ton carried out of the pit. A traffic jam can stop the mine. Why not replace one huge truck with 10 smaller ones? On paper, that sounds more flexible. If one vehicle breaks down, the others can keep working. But inside a mine, more trucks do not automatically mean more production. Every haul truck follows the same closed loop. It drives to the shovel, waits for a load, climbs out of the pit, reaches a crusher or waste dump, unloads, and returns. The timing must be carefully balanced. If too few trucks are assigned to a shovel, the shovel sits idle. If too many arrive, they form a queue. Now, scale that problem across an entire open-pit mine. A line of waiting trucks is not just inconvenient. Each vehicle may be idling, consuming fuel, occupying road space, and producing nothing. Smaller trucks also require more frequent exchanges beneath the shovel. The loading area becomes busier, intersections become more crowded, and dispatchers must coordinate far more moving machines. Mining engineers often model this system like a network of queues. The productivity of one machine depends on the timing of every other machine around it. One delayed truck can disrupt the sequence. A blocked ramp can affect several loading areas at once. Larger trucks reduce the number of vehicles required to achieve a target production rate. Fewer trucks mean fewer interactions, fewer loading exchanges, and less congestion. In a mine, traffic is not a side problem. Traffic is part of the production process. If the loop stops moving, the mine stops making money. The tires set the final limit. It is tempting to think the only thing preventing mining trucks from becoming even larger is engine power. Build a stronger engine, reinforce the frame, and increase the payload. But eventually, all of that weight must pass through 6 contact patches of rubber touching the ground. That is where the real limit begins to appear. The Caterpillar 797F typically uses enormous 59/80R63 tires. Each one must support not only the weight of the truck, but also its share of a payload approaching 363 metric tons. And the load is never perfectly gentle. The tires absorb impacts from rough haul roads, side forces during turns, and continuous heat generated as the casing flexes under pressure. Heat is especially dangerous. Tire manufacturers and mine operators use ratings such as TKPH or TMPH to account for payload, speed, distance, and heat buildup. A tire may be strong enough to hold the truck while stationary but still overheat when repeatedly carrying heavy loads over long haul cycles. That means a mine cannot simply add more power and drive faster. Higher speed produces more heat. More payload increases stress. Longer routes reduce the time available for cooling. The engine may be capable of moving a larger machine, but the tires must survive beneath it hour after hour. Frames, brakes, roads, and drivetrains also impose limits. But tires are among the most unforgiving. You can build a bigger truck. The harder question is whether you can build a tire that will live under it. Mining trucks are not enormous because engineers simply wanted bigger machines. They are the result of an entire system built around moving mountains at the lowest possible cost, one load at a time. Every giant shovel, haul road, tire, and loading cycle pushes them toward the scale. Click the next video to uncover another hidden engineering story. Like, subscribe, and tell us what surprised you most. Thanks for watching, and we will see you in the next one.